Okay, so today we're going to talk about phase diagrams. So our metals, when we combine to make an alloy, were silver and palladium. And this alloy is shown in this graph here. And this graph shows the relationship between temperature and weight percent. And you can see in the top portion of this graph here, it says liquidus, which is the liquid phase. And the bottom portion is a solidus, which is a solid phase. And if you look at the graph, from the graph, the high point on the temperature is 1554 degrees Celsius, and the lowest point is 961 degrees Celsius. So the phase diagram does not exhibit any allotropy, eutectic, hypoeutectic, hypereutectic, eutectoid, hypoeutectoid, hypereutectoid, peritectic, hypoperitectic, or hyperperitectic reactions. So next, to find the phase change cooling rate, we use the lever rule, and uh, the lever rule uses a tie line which connects the phases in equilibrium with each other, which can also sometimes be called an isotherm. And to calculate this cooling change, we use two main equations. The first one is WL, which is equal to C alpha minus C0 divided by C alpha minus CL. And all of these can be found in the table, or in the graph here on the left. So C0 is the middle, and CL is the left side, and C alpha is the right side. And the second graph, or the second equation that's used, is W alpha is equal to C0 minus CL divided by C alpha minus CL. And after we calculated WL and W alpha from our graph, you can see that the distance between CL between CL to C0 and C0 to C alpha were pretty much the exact same distance. So you can see after we calculated here, we get WL is equal to 1/2 and W alpha is equal to 1/2. And this shows that both distances were exactly the same. And that is how you find the relative change in the phase from cooling.